already taught you that for direct band-to-band semiconductors at equilibrium, generation rate of free electrons is equal to generation rate of holes, which is further equal to recombination rate of holes and recombination rate of free electrons. This equality sign comes because in direct band-to-band semiconductors, free electrons and holes always generate in pairs. Similarly, this equality sign comes because free electrons and holes always recombine in pairs. And this equality sign is because the semiconductor is at equilibrium. Now, in this lecture, we will discuss non-equilibrium case. We will assume that a pulse of photon beam is introduced on the surface of the semiconductor, disturbing its equilibrium with the new electron and hole concentration 2b n and p, where n is equal to n naught plus delta n and p is equal to p naught plus delta p, where n naught and p naught are the equilibrium, free electron and hole concentration values present just before photon bombardment. Remember that mass action law is valid for equilibrium cases. Therefore, square of intrinsic carrier concentration is equal to n naught into p naught but not equal to n into p. Since n naught and p naught are the free electron and hole concentration at equilibrium and n and p are non-equilibrium free electron and hole concentration. Delta n and delta p are the excess carriers which are produced because of photon bombardment. Remember that all the concepts which are related to excess carriers are very important. Majority of the semiconductor devices operate because of these charge carriers. For simplicity, we are again considering direct band-to-band semiconductors. Since the semiconductor is having direct band-to-band transition properties, therefore the recombination rate of excess holes and excess free electrons are also equal. Let Rn dash represents the recombination rate of excess free electrons and Rp dash represents the recombination rate of excess holes. Since the semiconductor is having direct band-to-band transition properties, therefore the recombination rate of excess holes and excess free electrons will also be equal. The probability of an hole and electron recombining is also constant with time. The rate at which electrons recombine must be proportional to the electron concentration as well as hole concentration. Therefore, we can write the net rate of change in electron concentration like where free electron concentration is a function of time equal to time independent thermal equilibrium concentration n naught plus excess carrier concentration, which is a function of time. Similarly, we can write for hole concentration. Also, the first term, which is alpha Ni square, is actually thermal equilibrium recombination rate. But since at thermal equilibrium recombination rate is equal to generation rate, we can also say that alpha R into Ni square is equal to generation rate at thermal equilibrium. Also, another important point is that since we have already considered that the semiconductor is of direct band-to-band type, therefore excess free electron concentration is equal to excess hole concentration. I am saying again and again that we are considering direct band-to-band semiconductor, and it may be possible that few of you may not understand the true significance of this semiconductor. I am recalling the concept about the difference between direct band-to-band semiconductor and indirect bandgap semiconductor. On the upper side, we have energy band diagrams, and in the lower side, we have EK diagram. In the right side, you can see that the minima of conduction band is having approximately the same K value for the maxima of valence band. These type of semiconductors have direct recombination, meaning that an electron in the valence band will directly go to the conduction band, resulting in generation of free electron and hole simultaneously. However, if we talk about indirect semiconductors, there are few energy states which are called as trap centers or recombination centers. And in the energy band diagram, these trap centers are represented by an energy state between band gap energy. So, sometimes when an electron in the valence band tries to make a transition to conduction band, then rather than going to conduction band directly, it goes to the trap center. Therefore, it creates hole but not a free electron. So, we can say that excess free electron concentration is equal to excess hole concentration for direct band to band semiconductors only. However, the same cannot be said to be true for indirect band gap semiconductors. I hope the point is clear to you. Now we will come back to our derivation. We will replace free electron concentration and hole concentration in terms of thermal equilibrium concentration and excess carrier concentration, which will result to you know that free electron concentration at thermal equilibrium is independent with time. Therefore, the differentiation of N naught with respect to time is 0. Similarly, we know that due to the mass action law, Ni square is equal to N naught into P naught. Therefore, these two terms will also cancel. And also, we have assumed the semiconductor is direct band to band type. Therefore, excess free electron concentration is equal to excess hole concentration. After modifying the equation, we will get this is a very important equation. Remember that we have assumed that the semiconductor is of direct band to band type. If the semiconductor is of indirect type, then we cannot put excess free electron concentration to be equal to excess hole concentration. We will assume two more assumptions. The first is the semiconductor is of p type, meaning that p naught will be significantly greater than n naught, and it will be easy to solve this equation if we limit the excess carriers to be very small compared to thermal equilibrium majority carrier concentration, and this particular assumption is referred to as low level injection, where the excess carrier concentration is significantly smaller than thermal equilibrium majority carrier concentration. Similarly, in the case of high level injection, the excess carriers become comparable or greater than thermal equilibrium majority carrier concentration. After putting the assumptions, we will get we have ignored N naught, and since excess carrier concentration is significantly smaller than majority carrier concentration, we have ignored the square of free electron concentration also. And after solving it, we will get this particular equation is written as free electron concentration at time 0 into exponential of minus t divided by tau Ne, where tau Ne is equal to 1 upon alpha r into P naught. which is called excess minority carrier lifetime. We have taken p-type semiconductor, but the suffix here is n, as the suffix is representing the type of minority carriers present inside the semiconductor, which is free electrons in case of p-type semiconductor. Similarly, if we have to solve this equation for n-type semiconductor, we will get excess minority carrier lifetime to be equal to 1 upon alpha r into thermal equilibrium free electron concentration. It is extremely important to remember this derivation because it is not necessary that the questions will be asked only from the final result, but they can also provide you data such that the assumptions are not valid and you have to solve these equations manually. Most of the questions in engineering studies require good skills in mathematics. Only a slight knowledge of core concepts are used. And if you observe carefully, the equation for direct band-to-end semiconductor without the assumption of low-level injection is also not very difficult. You can solve this equation if the low-level injection is not valid. The recombination rate can also be written as del N-T divided by excess minority carrier lifetime. For direct band-to-band semiconductor, free electrons and holes recombine at the same rate. Therefore, we can write recombination rate of excess free electron is equal to recombination rate of excess holes. For p-type semiconductor, we can also write del N-T divided by tau Ne. Similarly, for n-type, we have assumed that recombination rate and generation rate is independent of space coordinates. However, it is not necessarily true. The generation rate and recombination rate may be function of space coordinates as well.